Quantum physics is the branch of physics that explains how matter and energy behave at the smallest scales. To understand quantum physics, we must first contrast it with classical physics. Classical physics governs everyday objects, while quantum physics governs atoms and subatomic particles. At the quantum scale, the rules of physics become very different from what we experience in our everyday lives. One of the most fundamental concepts in quantum physics is wave-particle duality. This means that particles like electrons and photons can behave as both particles and waves simultaneously. This dual nature challenges our everyday understanding of reality and is best demonstrated through the famous double-slit experiment. The double-slit experiment begins with a source that emits particles, such as electrons or photons. These particles pass through a barrier with two slits and then hit a detection screen. When particles go through the slits, something remarkable happens. If we send them one at a time, they still create an interference pattern on the screen, as if they were waves passing through both slits simultaneously. This creates a pattern of alternating bright and dark bands, known as an interference pattern, which is a characteristic of waves. But here's where it gets truly strange. If we try to observe which slit each particle goes through by placing a detector at one of the slits, something remarkable happens. The interference pattern disappears. Instead, we see two distinct bands on the screen, as if the particles are now behaving like solid objects going through one slit or the other, but not both. This demonstrates a fundamental principle of quantum physics. The act of measurement affects the behavior of quantum systems. When not observed, particles behave like waves, but when measured, they behave like particles. This counterintuitive behavior is fundamental to quantum physics and challenges our everyday understanding of reality. It shows that at the quantum level, the act of observation becomes part of the system being observed. These fundamental concepts form the basis for understanding the strange and fascinating world of quantum physics. Heisenberg's uncertainty principle is a foundational concept in quantum physics. It states that we cannot simultaneously know both the position and momentum of a particle with perfect precision. This is mathematically represented as delta x times delta p is greater than or equal to h bar divided by 2. This means that the more precisely we measure position, the less precisely we can know momentum, and vice versa. Let's visualize this relationship. When we measure position with high precision, we have a very narrow distribution. But this forces momentum to have a wide distribution, meaning low precision. Conversely, if we precisely measure momentum, position becomes more uncertain. Quantum superposition is another fascinating principle where particles exist in multiple states simultaneously until measured. This is represented by the wave function, which contains all possible states a quantum system can be in. Schrödinger's cat thought experiment illustrates this concept on a larger scale. In this famous thought experiment, a cat in a sealed box exists in a superposition of being both alive and dead simultaneously. This continues until someone opens the box to observe the cat, causing the wave function to collapse to one definite state. Quantum entanglement is perhaps the most mysterious quantum phenomenon. It occurs when particles become connected in such a way that the quantum state of each particle cannot be described independently of the other. Einstein famously called this spooky action at a distance because it seemed to violate principles of locality. When two particles are entangled, they share a single quantum state. No matter how far apart they are, they remain connected. If we measure one particle to have spin up, its entangled partner instantly assumes the complementary state of spin down. This happens instantaneously, even if the particles are on opposite sides of the universe, seemingly faster than light. These strange quantum properties aren't just theoretical curiosities, they have real-world applications. Quantum computing leverages superposition to process information in ways classical computers cannot, potentially solving problems that would take traditional computers millions of years. Quantum cryptography uses the principles of quantum mechanics to create theoretically unbreakable encryption, where any attempt to intercept communication would disturb the quantum state and be detected. In medicine, quantum imaging techniques are pushing the boundaries of what we can see, providing unprecedented detail in medical scans by using entangled photons.